Unit 2, Mineralogy. Mineralogy is a branch of geology that deals with the study of minerals in respect of their mode of formation, physical, chemical, and engineering properties, and their occurrence, distribution, and uses. Important terms involved in mineralogy. First one, mineral. Mineral is a natural occurring solid state. It's a inorganically formed. It has definite chemical composition with a definite atomic structure. For example, ice is a mineral, but water is not a mineral. Then mercury and petroleum are minerals, even though they are in liquid state. There are more than 2000 minerals known to occur in the earth crust. Already in first unit, we see about what is the crust. Okay, minerals are generally occur some states like crystal, crystalline, and amorphous states. Crystal. A crystal is a solid that's having a definite internal atomic structure and is a distinct external geometric form that's called crystal. And crystallography. Crystallography is the branch of mineralogy dealing with the study of crystals. It is called crystallographic. And amorphous. Amorphous is a mineral is in powder form and is lacking both internal atomic structure and external geometric form. Okay, and then cement and concrete and bricks are the important construction materials whose constituent of minerals. Okay, hence the study of mineralogy plays a important role in civil engineering. Next, crystallographic. The branch of mineralogy dealing with the study of crystals and its formation is called as crystallography. Crystal. It is a solid bounded by a plane surface arranged in a regular pattern. Crystal is a solid bounded by smooth surfaces with a definite internal atomic structure and distinct external geometric form. For example, calcite, quartzite, etc. Symmetric elements of crystals. Crystals are studied and recognized by their symmetric elements. The symmetry elements of crystals is studies the following categories, that is plane of symmetry, axis of symmetry, and center of symmetry. What does it mean by plane of symmetry? A plane of symmetry of a crystal is an imaginary plane which symmetrically divides the crystal into equal arcs in such a way that one arc is the mirror image of other. That is called plane of symmetry. Next, axis of symmetry. An axis of symmetry of a crystal is an imaginary axis passing through the center of crystal, about which, if the crystal is rotated through 360 degrees, it will bring the same crystal face or any other configurations twice, thrice, or 4 times, or 6 times, whatever, into the same position in space. That is called axis of symmetry. Then center of symmetry. Center of symmetry, when an imaginary axis passing through a crystal from a point on one side a crystal meets the same point on diametrically opposite side of the crystal. Then the crystal is said to possess a center of symmetry. Center of symmetry may be or may not be present in a crystal. Next, how the minerals are formed. Generally, the crust surface having magma underground. Magma and lava is a molten material. That molten material converted to crystallization and is formed into a mineral. Then here, evaporation of the ground and release of the ground is converted into a solution. That solution is formed in a mineral formation. Is the mineral formations. Next, crystal systems. Crystal systems, there's having 9 crystal systems. One is isometric system and tetragonal system, hexagonal system, orthorhombic system, monoclinic system, and triclinic system. These are all the crystal systems. Generally, the crystal systems showing in the highest number of symmetry elements is called the normal class of the respective crystal system. First one is triclinic system. A triclinic system is characterized by 3 unequal crystallographic axes in which all the 3 axes are inclined in space with varying angles between them. That is, A is not equal to B, B is also not equal to C. That is called triclinic system. And next one is monoclinic system. Monoclinic system is characterized by 3 unequal crystallographic axes in which one of the horizontal axes is inclined towards the observer, making an acute angle with C axis. That is, A is not equal to B and B is not equal to C. That is, A and B is in equal to 90 degrees and C is less than greater than 90 degrees. That is called monoclinic system. And third is orthorhombic system. An orthorhombic system is characterized by 3 unequal crystallographic axes which are perpendicular to each other. That also A is not equal to B, B is not equal to C, but it's always perpendicular to each other. So alpha, beta, gamma is equal to 90 degrees. And tetragonal system. A tetragonal system is characterized by 3 imaginary crystallographic axes which are perpendicular to each other. But the vertical axis C is either longer or shorter than the other 2 equal horizontal axes. That is A equal to A1, A2, that is not equal to C. That is alpha, beta, gamma is also 90 degrees. And hexagonal system. A hexagonal system is characterized by 4 crystallographic axes, that is one vertical axis C and 3 horizontal axes, that is A1, A2, A3, in which the vertical axis is unequal and perpendicular to all the horizontal axes, and the 3 horizontal axes are equal and making an angle of 120 degrees. That is A1 equal to A2 equal to A3, but these 3 are not equal to C. And then alpha and beta is equal to 90 degrees and gamma is equal to 120 degrees. That is hexagonal system. Finally, isometric system. An isometric or cubic system is characterized by 3 imaginary crystallographic systems, that is A1, A2, A3, which are equal in length and mutually perpendicular to each other. That is called isometric system. that is A1 equal to A2 equal to A3, and alpha, beta, gamma is equal to 90 degree. So these are all the crystal system, fixed crystal system, that is isometric. Isometric, all the angles are equal to 90 degree, and triclinic system. Triclinic system is a inclined surface perpendicular to each other and vertical. This also A is not equal to B is not equal to C. And monoclinic system, orthorhombic system, tetragonal system, hexagonal system, and isometric system. These are all the 6 crystal systems. This is the short form. First one is, for example, of cubical system. That's all sides are equal, then all angles are equal to 90 degree. Tetragonal system, 2 equal sides, 1 unequal sides, and that's not equal to 90 degree. And hexagonal system, 3 equal sides and 1 unequal sides, when one angle is equal to 90 degree and 3 angle is equal to 60 degree. Orthohomral system, all sides are equal, but the angles are not equal to 90 degrees in all sides. Orthorhombic system, all sides are unequal and all are less than 90 degree. And monoclinic system, all sides are unequal and 2 sides are equal to 90 degree and 1 side is not equal to 90 degree. Triclinic system, all axes are unequal and all angles are also not equal to 90 degree. Next, physical properties of minerals. So minerals having some physical properties. What are these physical properties? That is color. Minerals having some colors and minerals having some streaks. So let's one by one. What is that? First, what are the properties? Let's see first. Color, streak, luster, hardness, cleavage, fracture, tenacity, specific gravity, structure, and some of the special properties. Special properties means like magnetism, phosphorence, fluorescence, like that. Okay, these are all some special properties. Out of this, color and streak and luster are the properties depending upon light, cleavage, hardness, tenacity. These properties depending upon the cohesion properties. First, we see forms and habits of minerals. Forms or structure habits. Forms represents the common mode of occurrence of a mineral in nature. It's also called habit or structure of minerals. To some extent, this is the function of the atomic structure of minerals, the forms of minerals. A lot of forms are there. Generally, it's divided into 3 categories. One is crystal form and crystalline form and amorphous form. These 3 forms, let us be in starting. Next, structure forms. First thing, lamellar form. Lamellar form is like that minerals appears a thin separatable layer that is called lamellar form. Thick leaf like shapes, that's example of mica. Next, tabular form. Tabular form is a flattened table. For example, calcite, feldspar, etc. Minerals appears as a slab uniform thickness that is called tabular form. Next, fibrous form. Minerals appears to be made up of thin thread. You are looking, see here, minerals are forms like a looking thin thread. For example, asbestos. Asbestos is the example of fibrous form, and bauxite is the example of piezolytic form. There is the minerals appears to be made up of small speckled grain. Oolitic form, for example of limestone. That is, minerals appears to be made up of still small speckled grain. Rhombic form. Minerals appears to be made up of rhombic form. For example, calcite. Next, granular form. Minerals appears to be made up of innumerable equidimensional grain of coarse or medium grain. That's called granular form. Example, magnetite and chromite. Next, bladed form. Kyanite is the best example of bladed form. It's looking like a cluster or independent lathe-shaped grains. That's called bladed form. And botryoidal form is looking like a smaller curved faces, like a bunch of grapes. That's called botryoidal form. Example, hematite. And acicular form. It's looking like a thin needles. That minerals is looking like a thin minerals. That is called acicular form. Example, natrolite. And columnar form. It's looking like a long slender prism. That's called columnar form. Example, quartz, apatite, etc. Prismatic form. Minerals appears as elongated independent crystals. That is called prismatic form. Example, quartz. And spongy form. It's looking like a porous minerals. It's having a lot of pores. That is called spongy form. Example, pumice. Crystal forms. So already let's see what are the crystal forms. Polyhedral geometrical shapes. For example, quartz, amethyst, pyrite, galena. These are all the best examples of crystal form. Then nodular form. Nodular form is a irregular shaped compacted body with curved surface. For example, limestone. Next, color. Next property, let's see about color. Color is due to the composition of minerals. In some others, it is imparted by the presence of trace elements, inclusions, atomic structures. The color of the mineral is due to absorption and reflection of light. Any object that appears white will absorb and reflect all the 7 colors of light. Any object that appears black will absorb all colors but reflect none of the colors of light. With respect to the property of color, minerals are classified into idiochromatic, allochromatic, and pseudochromatic. This is the examples of color. For example, graphite is a shining black color and hematite is a dark steel gray color. Amethyst is a coloring violet color. Okay, and calcite is in white color. Jasper is in red color. Olivine is a green color. Idiochromatic, mineral showing single and constant color. That's called idiochromatic colors. Allochromatic colors, minerals showing variable colors due to impurities present. For example, calcite, quartz, like that. Pseudochromatic, minerals showing false color when rotated. Examples, diamond. Okay, so these are all some of the examples of color. Color is determined by the chemical composition of minerals. Which minerals are rich, like that aluminum, calcium, sodium, magnesium. Then the minerals reflected light color. And the minerals rich in iron, titanium, nickel, chromium. These minerals are shown in dark in color. Atomic structure controls which components of white light are absorbed or reflected. White minerals reflect all components of white light. Black minerals absorb all components of white light. Green minerals reflect green light and absorb the others. Color is not particularly useful as a diagnostic property. The minerals show a wide variety of colors. Quartz can be transparent, white, pink, brown, purple, yellow, orange, and even black. Many minerals show very similar colors. Calcite, gypsum, barytes, fluorite, plagioclase feldspar, and olite are commonly gray or white in color. These are all some examples of color variation in fluorite. These are all the fluorite metal, but the colors varies. These are all the gray and white color minerals. Plagioclase, quartz, calcite, barytes, fluorite, gypsum. These are various minerals, but same in color. Here, the minerals are same, but various in colors. Next, streak. What is the difference between color and streak? That's why I'm again telling what is meant by color. Color depends on absorption of some and reflection of other colored rays or vibrations which compose ordinary white light. But streak, it is a color of powder of mineral produced on rubbing. It is determined by rubbing a mineral or unglazed porcelain plate. That is streak. The color of a mineral's powder obtained by rubbing a mineral specimen on an unglazed white porcelain title. Useful for identifying metallic ore minerals. Silicates generally do not mark the tile and have no streak. White minerals streak on a white tile will have a white streak. Any minerals harder than a tile is having no streak. Hematites, it gives a cherry or red in streak. These are some examples of streak. Quartz, its color in white, its streak also in white. Pyrite is a golden yellow color, but its streak is in black color. Hematite, that's it. Hematite is a color in cherry red color, but the streak is a brown color. These are all some examples of streak. Pyrite is in black color and hematite is a golden yellow color. Ornament, sulfur is in yellow color. Graphite is a dark blue color. Azurite is in blue color in streak. Malachite is a light green color in streak. These are all the some examples. Next property, luster. It is appearance given to a mineral by light reflected from its surface. That is called luster. Luster, the nature of reflection surface, the light absorption capacity of the mineral, the refractive index of the mineral. Types of luster: metallic luster, vitreous luster, resinous luster, pearly luster, silky luster, adamantine luster. For example, metallic luster is a metallic minerals, pyrite and galena. And vitreous luster is an example of quartz. Resinous luster is an example of opal, amber. Pearly luster example of talc. Silky luster is the example of gypsum. Adamantine luster is the example of diamond. And dull is having no luster. For example, chalk, bauxite, like that. This is the some of examples luster. For example, galena, gold, pyrite, and submetallic luster, magnetite, hematite, chromite, vitreous luster, quartz, dolomite, calcite, purely luster, talc, Muscovite mica, and gypsum, silky luster, asbestos, stainsper, resinous luster, open, adamantine luster, diamond. And next, transparency. Transparency is a mineral transparent when the outlines of the objects seen through it appear sharp and distinct. That is called transparency. When an object looks indistinct, that it is called as semi-transparent. Minerals which are capable of transmitting light but can't see through it are called translucent. Minerals which do not transmit the lights are called as opaque minerals. These are all the some examples of transparency. This is translucent, calcite, agate. Degree of transparency, for example, calcite, galena. These are all some of other examples of transparent minerals. Next, the forms of minerals. Already we see three forms: crystalline, crystalline. These are some examples. Next property is hardness. Hardness is a mineral is defined as the resistance offered by the mineral to any external force that tries to scratch on the mineral. That is called hardness. Hardness is a diagnostic and qualitative property of minerals. For example, talc is having the hardness number is 1 and gypsum 2. In 1822, Austrian mineralogist F. Moore proposed a scale of hardness, popularly known as it is Moore scale of hardness, in which he selected 10 minerals of known hardness and arranged them in increasing order of hardness from 1 to 10. Moore scale having 1 to 10 numbers. First, talc number 1 and gypsum number 2, calcite 3, fluorite 4, apatite 5, feldspar 6 or orthoclast. Feldspar or called as orthoclast. Quartz 7, topaz 8, corundum 9, diamond 10. The mineral numbers indicate its relative hardness. The scale ranges from 1 to 10. 1 is the softest and 10 is the hardest number. Suppose a mineral is not scratched by apatite and scratched by orthoclast feldspar. The hardness number of that mineral may be 5.5, where apatite having hardness number 5 and orthoclast feldspar having hardness number 6. The mineral scratched by orthoclast feldspar is having hardness number is 5.5. Some examples, window glass we are using in construction. We are having window glass that's having hardness number 5.5 and brass that is 3. Our fingernail it's having hardness number 1.5 to 2.5. Softest number is 1 and very hardest number is 10. Next, fracture. Mineral when breaks from cleavage plane, it forms a fracture. These are not linear nor parallel. Even fracture, uneven fracture, splintery fracture, conchoidal fracture, arclay fracture, or the different types of fractures. Even fracture is having smooth and flat surfaces. An uneven fracture is irregular with many ridges and depressions. For example, fluoride. Conchoidal fracture, broken surfaces, is having a concave surfaces like quartz. Hackley fracture, it's a highly irregular surface that's having native copper. These are the conchoidal fracture. It's a curved surfaces. And subconchoidal fractures, example, jasper, flint, agate. Next we see about cleavage. Cleavage is the property of mineral to split under the influence of force more or less parallel to crustal space. It may cleave in one or two, three, or more directions. That is called cleavage. Cleavage is having some of types: cubic cleavage, basal cleavage, prismatic cleavage, and rhombohedral cleavage. Next property is density. These are some of the examples of cleavage. It is in one direction, Muscovite mica, and prismatic two direction is orthoclast, and cubic three directions, example halite. Cubic three directions is the example of calcite. And density. Density is the specific gravity is the ratio of the mass of a substance to the mass of a reference substance for the same given volume. Specific gravity of minerals depends on their chemical composition and atomic structure. Specific gravity of minerals is determined by using either Walker-Steel theory or Joules's spring. Now let's complete the physical properties of minerals, and next class we continue what are the groups of minerals. Okay. Thank you.